Biochemical sedimentary rocks definition. Biochemical sedimentary rocks are a category of sedimentary rocks that originate from the accumulation of biological materials. These rocks are primarily composed of the remains of organisms such as shells, skeletons, plant material, and other organic debris. Over time, these biological materials accumulate in various environments, such as oceans, lakes, and swamps, where they undergo compaction and cementation, a process known as lithification. One of the most common types of biochemical sedimentary rocks is limestone, which forms predominantly from the calcium carbonate shells and skeletons of marine organisms like corals, foraminifera, and mollusks. As these organisms die, their remains settle on the ocean floor, building up thick layers of carbonate material that eventually harden into limestone. Chalk is a specific variety of limestone composed mainly of the microscopic skeletons of planktonic algae called coccolithophores. Another example is coal, which originates from the accumulation of plant material in swampy environments. Over millions of years, plant debris is buried by sediment, undergoing chemical and physical changes that transform it into peat and eventually into different grades of coal, lignite, bituminous, and anthracite, through the process of coalification. Biochemical sedimentary rocks are significant in geology because they often provide valuable information about past environments and the history of life on Earth. They can indicate the presence of ancient marine or swamp environments and often contain fossils that help paleontologists understand the evolution of life and past climate conditions. Formation of biochemical sedimentary rocks. The formation of biochemical sedimentary rocks is a complex process that involves several stages, including biological production, accumulation, compaction, and lithification. Here's a detailed explanation of each stage. 1. Biological production. Biochemical sedimentary rocks begin with the production of organic materials by living organisms. These materials can include shells, skeletons, plant matter, and other organic debris. In marine environments, organisms such as corals, mollusks, foraminifera, and plankton produce calcium carbonate, CaCO3, structures as part of their shells and skeletons. In terrestrial environments, plants produce organic matter that can accumulate in swampy areas. 2. Accumulation. After these organisms die, their remains settle and accumulate in various environments. In marine settings, the calcium carbonate structures sink to the seafloor, forming layers of sediment. In swampy terrestrial environments, plant debris accumulates in thick layers. Over time, these accumulations can form substantial deposits. 3. Compaction. As more layers of biological material accumulate, the weight of the overlying sediments exerts pressure on the lower layers. This pressure causes compaction, where the sediments are squeezed together, reducing the spaces, pores, between particles and expelling any trapped water. Compaction is crucial in transforming loose sediments into more solid forms. 4. Lithification. Lithification is the final step in the formation of biochemical sedimentary rocks. It involves two main processes, cementation and recrystallization. Cementation, dissolved minerals, often carried by groundwater, precipitate and fill the pore spaces between sediment particles, acting as a glue that binds the particles together. Common cementing agents include silica, CO2, calcite, CaCO3, and iron oxides. Recrystallization. Under the influence of pressure and chemical processes, the original minerals within the sediment can change in structure and composition. For example, aragonite, a form of calcium carbonate, can recrystallize into the more stable form, calcite. This process can further solidify the sediment into rock. Examples of biochemical sedimentary rocks. Limestone, formed primarily from the calcium carbonate shells and skeletons of marine organisms. Over time, these accumulations can create extensive limestone deposits. Specific types of limestone include chalk, which consists mainly of microscopic coccolithophores, and fossiliferous limestone, which contains visible fossil fragments. Coal originates from the accumulation of plant material in swampy environments. Plant debris is buried by sediments and undergoes a series of transformations through peat, lignite, bituminous coal, and finally anthracite. Each stage represents an increasing degree of compaction and carbon content. Chert often forms from the silica-based skeletons of microscopic marine organisms like diatoms and radiolarians. These organisms accumulate on the ocean floor, and their silica content eventually forms chert through recrystallization. Significance of biochemical sedimentary rocks. Biochemical sedimentary rocks are essential for several reasons. Paleoenvironments, they provide valuable information about past environments and climatic conditions. For example, limestone formations can indicate ancient marine environments, while coal deposits point to historical swampy regions. Fossils, these rocks often contain fossils, which are crucial for understanding the evolution of life on Earth. Fossiliferous limestones, for example, can be rich sources of information about marine life in different geological periods. Economic resources, many biochemical sedimentary rocks are important economic resources. Limestone is widely used in construction, agriculture, as a soil conditioner, and industry, in the production of cement and glass. Coal is a significant energy resource, providing fuel for electricity generation and industrial processes. Understanding the formation and characteristics of biochemical sedimentary rocks is fundamental in geology, offering insights into Earth's history, the evolution of life, and the processes that shape our planet. Properties of biochemical sedimentary rocks. Biochemical sedimentary rocks possess a variety of properties that make them unique and distinguishable from other types of sedimentary rocks. These properties can be categorized into physical, chemical, and biological aspects, each offering insights into the conditions under which these rocks formed and their subsequent history. Here is a detailed exploration of these properties. Physical properties. Texture. Grain size. The grain size in biochemical sedimentary rocks can vary significantly, ranging from fine-grained, such as in chalk, to coarse-grained, as seen in fossiliferous limestone. The grain size is influenced by the types of biological materials that make up the rock and the environment of deposition. Shape. The particles in biochemical sedimentary rocks can be well-rounded or angular. For example, the shells and skeletal fragments in limestone are often broken and abraded, leading to various shapes. Sorting. Sorting refers to the uniformity of grain sizes within the rock. Biochemical sedimentary rocks can be well sorted or poorly sorted, depending on the energy and consistency of the depositional environment. Porosity and permeability. Porosity. This refers to the percentage of void spaces within the rock. Biochemical sedimentary rocks can have high porosity, especially if they contain a lot of loosely packed biological debris. Permeability. The ability of a rock to transmit fluids. Rocks like limestone can have high permeability due to the presence of interconnected pore spaces and fractures. Color. The color of biochemical sedimentary rocks can vary widely. For example, limestone is typically white to gray, but impurities can impart colors such as yellow, brown, or black. Coal ranges from brown, lignite, to black, anthracite, depending on its type and carbon content. Chemical properties. Mineral composition. Carbonates. The primary component of many biochemical sedimentary rocks like limestone is calcium carbonate, CaCO3, which can occur in the mineral forms of calcite or aragonite. Silica. Chert is primarily composed of silica, CO2, derived from the skeletal remains of marine organisms like diatoms and radiolarians. Organic matter. Coal is composed predominantly of carbon, along with varying amounts of other elements such as hydrogen, sulfur, oxygen, and nitrogen, depending on its grade and type. Solubility and reactivity. Carbonates. Rocks like limestone are highly reactive with acids, which makes them easily identifiable in the field using a dilute hydrochloric acid test. This reactivity is a result of the calcium carbonate content. Silica, chert, being composed of silica, is much less reactive with acids compared to carbonates. Biological properties. Fossil content. Biochemical sedimentary rocks often contain fossils or fossil fragments. Fossiliferous limestone, for example, can be rich in visible remains of marine organisms such as corals, brachiopods, and mollusks. These fossils can provide critical information about the age and environment of the rock formation. Coal may contain plant fossils, including leaves, stems, and roots, providing insights into the types of vegetation that existed in the depositional environment. Organic content. Coal, in particular, is noted for its high organic content, originating from the accumulation and preservation of plant material. The degree of organic content and its state, e.g., peat, lignite, bituminous, anthracite, reflects the extent of coalification, which is the process of transformation under heat and pressure. Mechanical properties. Hardness. The hardness of biochemical sedimentary rocks varies. Limestone is relatively soft, with a Mohs hardness of around 3, making it susceptible to weathering and erosion. In contrast, chert is much harder, with a Mohs hardness of about 7. Durability. Durability depends on the composition and the environment in which the rock formed. Limestone, while widely used in construction, is susceptible to acid rain and weathering due to its solubility in weak acids. Chert, being more durable, is resistant to chemical and physical weathering. Economic importance. Construction material. Limestone is extensively used as a building material and in the manufacture of cement. Its ease of extraction and workability make it a preferred choice for construction. Energy resource. Coal is a crucial energy resource, used primarily for electricity generation and steel production. The different grades of coal are utilized based on their energy content and carbon concentration. Industrial uses. Limestone is used in various industrial processes, including as a raw material in the production of lime, chow, an essential component in the chemical, paper, and steel industries. Chert is used in the production of tools and abrasives due to its hardness. Geological significance. Indicators of past environments. Biochemical sedimentary rocks are excellent indicators of past environments. Limestone formations can indicate ancient shallow marine environments, while coal deposits are indicative of historical swampy or peat-forming regions. Stratigraphic markers. The presence of specific fossil assemblages in biochemical sedimentary rocks can help geologists correlate rock layers across different regions, aiding in the reconstruction of geological history. Understanding the properties of biochemical sedimentary rocks is essential for geologists, paleontologists, and engineers. These properties not only provide insights into the formation and history of the rocks but also determine their practical applications and significance in various fields.